All right. We are going to get into capacitors today. We're going to talk some more about electric potential. What is a word that's synonymous with electric potential? Voltage. So charge, electric potential, capacitors. Now, we have a picture here to start. Once again, it'll probably come up, but it's a good illustrative picture. We know that if I have a charge in an electric field, if it's a positive charge, it's going to have a force in the same direction as the electric field because force is Q times E. If it's a negative charge, it's going to have a force opposite to the electric field. So in this situation, I have force vector equals Q E vector is to the right. If the charge moves from here to here, some distance d, then there's going to be work done on the charge. How do I calculate the work? Work is always blank times blank. Okay, force times the distance parallel. So I put a dot product between them because it's only the parallel parts. Now with my picture, the distance moved was parallel to the force. So that means that the electric field will do a positive work of the force times the distance, which will be equal to QED. What happened to the vector signs? Because the electric field and the distance were parallel, the dot product of electric field dot D was just electric field times D. So it's because of the parallel that the vector signs and the dot product disappeared. What if instead of moving that way, it had moved this distance B? Then what would I get for the force dot B? If they're perpendicular, I get 0. So there's no work to move perpendicular to the electric field. Hence, there's no change in electric potential energy if I move parallel, which means no change in electric potential. So the voltage is going to be the same if I move parallel or perpendicular to the electric field lines. It only changes if I move parallel to them. And it changes by QED, which generally when you say QED, you mean quadrant demonstratum. What was to be shown has been. But here, it doesn't even stand for quantum electrodynamics. It's charge times electric field times distance. So that's the work. How does work relate to potential energy? Okay, we define change in potential energy as minus the work by a conservative force. This electric force is conservative, means it'll give us back energy, and so we can define a potential energy that's minus that work conservative. So the change in potential energy is equal to minus QED. Well, now that I have that, I can go to a couple more things. What's the change in voltage? What's the definition of change in voltage? It's always the change in potential energy over the charge. So the voltage or electric potential change, notice it's the change in electric potential or the change in voltage, is change in potential energy over Q, which means it's going to be it's minus ED. Why minus? Well, that just has to do with the direction you went. If you go parallel to the electric field, you're going to have a drop in voltage. If you go opposed to the electric field, you have a rise in voltage. Hopefully I said that right. If you go with the electric field, it drops. If you go against it, it rises. Now, the final thing in this picture is this. And you're like, where does that come from? Well, that comes from if energy is conserved, then change in kinetic energy plus change in potential energy equals 0. So change in kinetic energy equals minus the change in potential energy. And then you look at this and you say, wait, what? There's no minus sign in this picture. Right? In that circle equation, there's no minus sign. Really, there should be. If the potential energy of the charge drops, the kinetic energy rises. That was just written on the magnitude and not paying attention to the direction. So the equation has a minus sign error there. It's important to point out. And the same would be true for the gravitational. If your change in potential energy gravitationally is positive, that is if it goes higher, it's going to slow down. It's not going to speed up. So there should have been minus signs both here and here in this diagram because it comes from conservation of energy. So that's, in a nutshell, 3/4 of today's lecture is going through these ideas. So now let's look at it a little more slowly, starting with a question that we ended last class period with. A point charge always naturally moves to a position of lower potential energy. What does this tell us about the natural motion compared to electric potential? I see Boss has answered. Yay, Corso answered. Everyone but Brandon. 33. All right. Two, 1, 15, 2. It showed me the numbers, but then it did some other things it shouldn't have done. Last class period, it just crashed on us. Yay. Okay, so we had a pretty large proportion that went with the answer we described in class on Wednesday. We have the point charge naturally goes to lower potential energy, which for a positive charge, potential energy is going to be lower when it goes with the electric field. And so it's going toward lower voltage based on the last page went through all of that. But positive charge is going to go toward negative charge, which is lower electric potential. Negative charge is attracted to positive charge. It's going to go the opposite direction. It goes toward higher electric potential. So just think about the electric potential as charge if you're getting things confused. Negative charge has a negative electric potential compared to positive charge, and a positive charge wants to go to the negative charge. Okay, so electric field points in the direction of decreasing voltage. We saw that here when I did this work. We have low voltage, high voltage, and the electric field is going from the high voltage, the positive charge, to the low voltage, the negative charge. A simple problem, like many that you've had in homework, a battery-powered lantern is switched on for 5 minutes. During this time, the electrons with total charge of minus 8.0 times 10 to the second coulombs, or minus 800 coulombs if you prefer, flow through the lamp. 9,600 joules of electric potential energy is converted to light and heat. Through what potential difference do the electrons move? Well, based on the work I did before, we saw that the change in potential energy was equal to, let's see, this one here is having to do with voltage, so it doesn't have, well, that's the definition. Change in potential, and there's no minus sign there, thinking the wrong thing. Change in potential energy is Q delta V, the charge multiplied by the change in voltage. So in this problem, I was given the change in potential energy, that is 9,600 joules. I was given the charge, minus 800 coulombs. So if I want to find the change in voltage, what is it? Okay, it's going to actually be the other way around. Have to divide both sides by Q to get delta V alone. And so it's going to be change in potential energy divided by charge. So that's just going to be 9,600 joules over minus 800 coulombs. Now I put the minus 800 coulombs and positive 9,600 because those are the numbers that were given to us. We have 9,600 that is converted. So 9,600 goes out of electric, and so we're going to have that as a drop for the for the energy in the battery. It's going to be a rise for the light and heat. So whether it's going to turn out to be a positive or a negative change in potential energy and thus change in voltage, we would have to worry about what the sign is. All I really care about is what's the magnitude. So I'm just going to put absolute value signs. And so I just get 9,600 divided by 8 is 12 volts. So it's a 12-volt battery. Turns out that was a real simple problem, huh? All you had to apply was this one equation in red. Change of potential energy is Q delta V. But it relates some important things, and we start to get a better feel for what voltage means. When we say, the voltage times the charge that went across that voltage tells us the energy that was transformed. This here, we went through all of this last class period, so I'm going right over it. Superposition of potentials. We talked about electric fields and how you find the electric field due to more than one charge. And I don't remember if I gave you a homework problem, but I know the supplemental homework had problems where you have, and Angelina, this you probably don't know unless somebody's told you. I lean heavily on the supplemental homework problems. They are not required for you to do. They're just there like for review problems to practice on. But I lean heavily on those for the tests. So a lot of the test problems are fundamentally the supplemental homework problems. So looking over those can help you prepare for the test. Okay, so I know I had a couple there that had you adding electric fields. And when you add electric fields, it's kind of a nuisance because you're adding vectors. Adding vectors adds a few levels of complexity. Electric potential is a scalar, just like work and energy are scalars. And when you are dealing with multiple charges and you want to find what's the total electric potential, you simply add the scalars. So the superposition of potentials is add them up. They're just numbers with units but no direction, so they're easy to add and subtract. For that reason, when we do physics, we really prefer to work with the electric potential because it's working with a scalar. And you can always determine what the electric field is from the electric potential. It's just a derivative. Just a derivative. So this is saying if I have a whole bunch of point charges, I just add up the voltages due to each point charge. So I add up the KQ1 over R1 plus KQ2 over R2 until I've added up all the point charges. So you can have a simple problem like this. I have 3 charges here. It tells me the charges and the locations. Find the electric potential at point A. So I find the electric potential here. I'm going to have V1 equals KQ1 over R1. R1, that's the distance from here to here, is 2 centimeters. And so that's going to be whatever Q is times K over 2 centimeters. And then I do this one here, which is square root of 5 is what R2 is. And this one here, square root of 2 is I got 2 and 3. That's 3. This is 2. And so I just get those distances and I put them all in. V total is equal to K times Q1 over R1 plus Q2 over R2 plus Q3 over R3. So it's not a hard calculation. All you would do now is put in numbers. I don't care to put in the numbers because the work was simple. So find the voltage, not so hard. And then it says a point charge of this size moves from A to B. And it says, what's its change in electric potential energy? Now that's a little more complicated. It has another word in there, energy. How would I find the change in potential in electric potential energy going from point A to point B? We just had an equation. Change in potential energy equals? No, not negative. I was wrong when I put the negative. It's Q delta V. So change in potential energy is Q delta V. I just calculated the voltage at point A, so I'll need to calculate the voltage at point B, and then I just say, the charge multiplied by the change in voltage is my change in potential energy. So I go through the same process of calculating the V, get the difference. Now, one thing this didn't say was what path it takes. Will it make a difference what path it takes? What if instead of doing the straight line like I drew, it goes up to here, then down to here, then over to there, and then back to here? Is that going to be a different change in potential energy? Okay, Gila has an answer. Well, Gila is the only one who answered, so I'll go with her answer. She said no, and she's right. It's like asking if I take this pin and I move the pin from there to here, its change in gravitational potential energy, is it different if I do it by going like this or compared to going like this? Doesn't matter what the path is, the change in gravitational potential energy was just mg times the change in height. It's the same thing for any conservative force. It doesn't matter what the path is, only the starting and ending points. Now to some fun rules. The potential due to a spherical conductor. Your field outside of a conductor acts as if all the charge is at the center, if it's spherical in shape. So you have a charge with charge spread on it, it'll spread around and act as if all the charge is at the center. And so the electric potential due to a conducting sphere is going to be the same calculation as it would have been if you had a point charge. So if you have a conducting sphere, has to be conducting. Now we have 3 people in the Physics 252 class, and they have a calculus assignment that's due on Tuesday. And in that problem, they have spheres that are not conducting. They're insulating. What's the difference in a conducting sphere and an insulating sphere? The charge in an insulating sphere is what? It's stuck. It can't move around. And so in their case, the charge is going to be distributed differently. If it's conducting, the charge is going to all be on the outside, and you can treat it as if it's the center. For their case, if it's spherically symmetric, they can still treat all of the charge as if it's at the center, but calculating the total charge is a little more difficult. They actually have to do an integral to find the total charge. So if I have a conducting sphere, solid sphere made out of iron, the electric field inside, I said, is 0. Remember when I argued about why the electric field inside a conductor should be 0? It's going back a week, I think. How many people remembered that the electric field inside a conductor is 0? Okay, we at least had 2 people that remembered that. Yeah, Edika.
I think it was because you said that it would be impossible because if it's 0, it can't have any fields going in. Or maybe I'm just kidding.
Well, that's relevant. That was for a hollow one. That was, I think, Wednesday when I talked about that. But for a conductor, if the electric field inside the conductor was not 0, then electrons that are in the middle would have a net force, right? Because the electric field force is QE. And so the electrons would be pushed and moved. So you wouldn't be in equilibrium. You can only reach equilibrium when the conducting electrons that are in the middle aren't pushed anywhere. So the net force is 0, which means the electric field has to be 0. So the electric field is going to have to be 0 if you have a conductor inside of the conductor. Hence this picture here showing electric field is 0 until you get to the radius of a spherical conductor. Now it has to be 0 inside any conductor regardless of the shape. But this here is for spherical conductor. So once you get outside, you have V equals KQ over R squared. Well, got to use lowercase r. So it's the same function as you would have had if it was a point charge at the center. So no electric field until you get to the surface, then it drops. Now for the electric potential for the voltage, if there's no electric field, if a particle moves in a region with no electric field, how does its potential energy change? Let's say an electron moves inside the conductor with 0 electric field. How does its potential energy change? It doesn't. Because the potential energy is going to be the force, 0, dotted to the distance traveled. As long as that force is 0, then the change in potential energy is 0, so the voltage remains constant. So the voltage inside is going to be constant everywhere. Didn't say 0 everywhere, just it's constant everywhere. But when you get to the surface, that should have been an E, by the way. You have V is equal to KQ over R. And so since it has this value right here, then it stayed constant throughout. So the voltage was not 0 inside of the conductor. The electric field was 0, but not the voltage. And so the same would be true if you're inside of a Faraday cage. Your voltage can move around, but the electric field is 0. You don't have anything that's causing charge to flow through you. Now, a lot of people are interested in biological systems. I imagine the majority of the people here are pre-med, pre-dent, pre-PA. And so those people care a lot about the biological applications, right? They tend to say, why do I have to take physics? I'm not going to be studying physics. I'm going to be studying biology. Well, here's an example of where physics applies in medicine. You have the body running as basically an electrical machine. We have electrical impulses that make our muscles contract. We have electrical impulses that carry signals through our nerves. And so the voltage differences, potential difference across the cell membrane, is part of how our body communicates. So this is just an example. Nerves, you have some nerve here, and you have the electrical signal coming through, the action potential, the rest of it. When a signal goes, like, something happens, I stick my finger in hot water, and I have a signal that tells my brain, ooh, that's hot. That was transferred by electrical signals going down these nerves. And so the body is using electricity, using the thing we're talking about to measure what's going on. And of course, much more important to many of us, the electrocardiogram. I'm sure many of you have had electrocardiograms. Probably the most unpleasant thing about the electrocardiogram is that they shave your chest first. Well, they shave patches, so you look like you've got something really funky going on. Why? Because they want to make good contact. And of course, if they just put a nice good glue on there and glue it on, and they leave the hair in place, it's really going to be painful when they take it off. So they shave it, and then it's really unpleasant as it grows out, just for the record, for people who might have a hairy chest. So what's the point of an electrocardiogram? Okay.
To check the heart and see how it beats by different ways.
Okay. The most fundamental thing is the first part she said. She said more. The most fundamental thing is to check to see if the heart's beating. But then they check for more things. So like as an EMT, the only EKGs I did was we had back then, at least in California back then, we had our defibrillator also was EKG. And so you put it on, and so, light on the right, smoke over fire. Everybody learned that, right? Okay. IRR people, you learned light on the right, smoke over fire. Yes? No? You just put the lead on randomly and it's white on the right, yeah. White, black, red. Anyway, you put those on, and ours would show us a simple EKG showing what's going on. The one that we're most used to seeing, like you go to the hospital, what you see on the monitor. And we'd look at that and we'd say, oh, look, it's a normal sinus rhythm. Or, oh, no, oh, crud, all these different rhythms. And then we would have to decide, are we going to shock this person or not? So let's start with simple things. The heart is essentially a muscle. And the muscles contract when they have electricity pass over them. They depolarize. And so they contract when you have electricity go through them. And what you're measuring here is the electrical signals from that electricity going through the muscle. So if you get no electrical signal, what does that indicate? Yeah. That's what we call asystole. They don't have any electric rhythm to make the heart beat. That's bad. That is not consistent with life, as we say. But then you have other things that can go on. So here's a picture of something much more complicated than what we do as EMTs. Notice this has a whole bunch of different connectors they put on. And then you have a few more for the whole body. Oftentimes people cheat on those. They're like, I don't need a left leg and a right leg. In medicine, they consider a lead any pair. So if you look at the picture just on the chest, you have 1, 2, 3, 4, 5, 6. What? 6 of them, right? No, 7 of them. So 7 of them, any 2 of those would be considered a lead. So there's a lot of leads. And if you go to the hospital and you have a full EKG, they say it's a 12 lead. They're looking at the electric signals between 12 different places because they want to see how the voltage is changing between, here and here, here and here, here and here, and so on. Here's a picture of the heart. My EMT teacher made a much easier heart. Good enough? Of course, your heart has different chambers. And you have to have a place for blood to come in. And then you have a couple valves. And you have to have a couple places for blood to go out. And let's see. I can't remember where the pulmonary arteries and veins are, so let's forget about those. So that's the basic heart that I learned as an EMT. How many people are EMTs here? Okay, so we have a lot. So a lot of people have gone through this. The heart is broken up. You have the two upper regions are the atria. The two lower regions are the ventricles. I don't know why I care, but I do. Historically, there's another name for the atria. They were previously called the auricles. Just in case you care, the auricles. You have the right side is anatomy. You always take the person's body and you just look at it, and the right side is the person's right, so it's on your left. You have the superior vena cava here, the inferior vena cava. Blood comes in, goes into the heart like that. Goes into the right atrium. And what is the right atrium? I'm leaning on my EMT folk. What is the right atrium? What's its basic purpose? That's actually a secondary function. Its primary function is just a place to store deoxygenated blood that the body has used. And then you have a valve there. What is that? The tricuspid? Yes. So it goes through that tricuspid into the right ventricle. You do have an electrical signal that goes over the atrium and makes the atrium pump. And so when I talk about electrical signals, the whole point of doing this, we'll get to that. But the atrium pumps blood. If your atrium is dead, then your cardiac efficiency drops by about 20%. If the atria are nothing but empty chambers with no pumping ability, you drop to about 80% of normal function. So it's not debilitating. That's why I said it's a secondary function. It is kind of important to push it through, but not vital. Okay, then you have the right ventricle pumps blood out into the lungs, and then it returns from the lungs to the left atrium, drains through the bicuspid valve into the left ventricle. The left ventricle is the big, meaty, muscular part of the heart that pumps the blood out through the arch of aorta. I really should have put the aorta coming down further so it at least, I meant to change that to red. Oh, perfect. At least put it so it comes down to the ventricle, and the ventricle pumps it through the body. Now, that's basic anatomy stuff that, frankly, I only know because I took EMT class. The physics stuff, the stuff I know better, is the electrical signal. You have up here a place that we call the SA node. SA is sinoatrial. I think it's spelled SINO, but it could be SINAL, I don't know. But you have the sinoatrial node. That's where the electrical signal that makes your heart pump starts. So you have an electrical signal that comes there to SA node, and then it goes through the muscle of the atria, both sides. So that signal then is going all through. It's a very complicated physics problem because the electrical signal is going all through the atria. And as it goes through, it causes a depolarization of the muscle. That depolarization is the same thing that happens when I send an electrical signal to my bicep and goes, right? It makes the atria compress. And so that's the pumping action that's going on in the atria. And then all of that electrical signal is actually collected at another node. And so we call that one the AV node. The AV node, the atrioventricular node. It's the connection between the atria and the ventricles. So you have electrical signal that first goes through the atria, goes to the AV node, and the AV node actually has a little delay. And then it sends an electrical signal down the bundle of His. So that's the bundle of His. And if you don't know your anatomy, you call it His. And then you have these little Purkinje fibers that go into the ventricle and put the electrical signals into the ventricle for it to depolarize. So it's a rather complicated system. Now, God has built us with some backups. Let us say that your atria are dead. If they're dead, that means you don't have the depolarization. You could have a signal coming to the SA node, but you don't have any depolarization. You don't have the conductivity. Nothing happens. Do you die then? No, you don't. Because that AV node is sitting there saying, where's my signal? And if it doesn't get a signal, it will tell the heart to beat about 40 times a minute. It's going to say, I'm not getting anything, but if the heart doesn't beat, this sucker's going to die. So go ahead and beat. So the AV node can actually keep you going, but you have a much lower heart rate. And of course, we call that bradycardia, right? Bradycardia is a slow heart rate because you're not getting that signal through the atria. What if, of course, you have a bundle blockage? 1 year, oh boy, it was about 7 years ago, my grandmother suffered a third-degree bundle blockage. A bundle blockage is when you have the electrical signal doesn't go through the bundle of hips. Your body's not telling the ventricles to pump. And that's really important. Well, you still have, your body will send a signal for the heart to pump about 20 times a minute if it's not getting the signal through the bundle of hips. And so your heart rate drops even more at that point. Your heart rate at about 20 beats per minute or less is probably not enough to stay conscious. So at that point, people go in and out of consciousness. But your body's still going to try to keep you alive. Now, these signals here, some people here can probably read an EKG. Let's just talk about this. This is the normal sinus rhythm. Not sinus is in up here, but sinus is in following the signals coming, from the sign. I don't know my anatomy to know what it actually is, but the signals that should be coming to the SA node. And so this here, the first piece is the P wave. So it's called the P. And that P corresponds to depolarization of the atria. Depolarization is when the muscle is contracting because of the electrical signal. So that P wave is showing you, oh yes, their atria are actually working. It's pumping blood with its small efficiency. Then you have this complicated piece. That's called the QRS complex. It's three waves or three things going on in the heart at once. One is the repolarization of the atria. And so the repolarization of the atria is causing a general downward curve as it repolarizes. And then you have the depolarization of the ventricles. That's causing the big push of blood. And I don't remember, maybe it's only two things, maybe it's just those two things. But that's what the QRS complex is. It's the recovery of the atria and the pumping of the ventricles, pushing blood from the right side of the heart to the lungs, so deoxygenated blood goes to the lungs for gas exchange, and then pumping the oxygenated blood from the left side into the rest of the body. And then the final wave here in my simple physics version is the T wave, which is the repolarization of ventricle. Now that's all fine and good until something goes wrong. Here about 11 years ago, something went wrong for me. And they look at different leads. I told you multiple leads. And I had the T wave doing something like that. Now, he's actually inversion on lead 3, I think is what it was. But my T-wave was doing the wrong thing. And what that indicates is that I wasn't getting enough oxygen to my heart. And, through a bunch of measurements, what they found was I wasn't getting blood through my lungs. I had a bunch of blood clots blocking the blood from going through my lungs. And so the right side blood pressure shot up to 3 times what they're supposed to be, and blood was not getting well oxygenated, so the heart was short on oxygen, hence that problem. So it was very, very beneficial to me that people have studied these things and know what they mean. They could take that to then know, oh, he's got blood clots filling his lungs. We've got to do something to get those blood clots out. So this is normal sinus rhythm. If something goes wrong, you could have like atrial fibrillation. Atrial fibrillation occurs when, and once again, I lean heavily on my EMT teacher, when the electrical pathways don't reach the AV node. They come from the SA node and they go into the atria, and then they start doing things like going around in loops. And there's a lot of physics on actually trying to model how current can flow through the heart. But if you have the current just going in loops, you no longer have a coordinated rhythm. You just have the atria, as my EMT teacher said, just sitting here and jiggling. But the jiggling is not doing any pumping. Now, of course, atrial fib isn't going to kill you because the atrium doesn't do all that much for you. Ventricular fibrillation, when you have that thing going on in the ventricles, when the ventricles are just quivering, you got a real problem because you're not pushing any blood through the body. What do we do when we see bad rhythms? Now, EMT people, you guys should answer this. What do you do if you see a bad rhythm on an EKG? You see a doctor? Okay, maybe it's like it is in California now here. They took away our defibrillators and gave us dumb defibrillators. Now, when I say dumb, I mean made for dummies. Probably a smarter defibrillator, but made for dummies. It no longer showed us what the EKG looked like. I didn't have to learn. I learned at one point what AFib looked like, what VFib looked like, and so on. And I had to know which ones are shockable and which aren't. But some rhythms are shockable. That is, you could shock the person and they might become more living, more compatible with life. Some are not. Some shocking is not going to help. And they have a problem with EMTs just saying, I'm going to shock this sucker and not paying attention. And so they took them away and gave us ones that would just, you put it on, it measures, it analyzes, and it either says, shock indicated, stand back, or no shock indicated. You don't shock every rhythm, but some rhythms you do. Why do you shock them? This is a big electrical item, and you depolarize by sending current through. You make the muscle contract. And the idea of the shock is maybe I'll be able to stop the heart. The whole goal of shocking somebody starts with, I want to stop their heart. Doesn't that sound a little scary? I mean, because you're thinking, stop the heart. What does it mean if my heart stops? I die. But the thing is, you want to stop the heart because hopefully, maybe, it will restart on its own and shift to a rhythm that's compatible with life. So you only shock the rhythms that are incompatible with life in hopes that they will convert to ones that are compatible with life. And so you shock them. You start with a fairly low energy. Some of them, they measure the energy in kilojoules. Some of them, they measure it in volts. Well, volts is not energy, right? That's energy per charge. And the energy is going to be the voltage times the charge that's transferred. But you can still just take the numbers as scales. And it starts with the lowest voltage or the lowest number of kilojoules that they figure might work. And you shock them, boom. And of course, the person is going to have a whole lot of muscle spasms when you shock them, because even though you're shocking them across the heart, you're going to have current that flows through other parts of the body and makes other muscles contract. And so you're making lots of muscles contract by putting that electricity across the heart. So you make electricity flow across the heart, and it depolarizes the heart. The whole heart goes, hoo-ah! and then hopefully it'll relax and start working again. If the heart doesn't stop and start up again, then you raise it to a higher voltage level and you do it again. And if it still doesn't do anything good and doesn't kill them, you raise it to your highest voltage level and do it again. And now, protocol may have changed. I last recertified 15 years ago. What do you do after 3 shocks with your protocol? Stop in? No. EMTs.
By then you should be at the hospital.
Wow.
That's anymore, and it's not treat, it's just get to the hospital.
Well, in Angling Community Ambulance, we went from Lake Berryessa to either St. Helena or Queen Valley Hospital, and it's an hour drive. We're not going to be at the hospital by that time. And so our protocol was you shock them 3 times. If they still haven't converted, you do CPR for, I think it was a minute, and then you just do another set of 3 at highest voltage. And then if nothing's happening, you do CPR for another minute. Final set of 3 at highest voltage. If nothing's happened after 3 sets of 3, then you just do CPR because you got a dead person. And by the way, anyone who's worked on an EMT or on a rig knows no one ever dies in an ambulance. Only the freshest of green rookies would ever say the person died in the ambulance. Because if the person dies in your ambulance, then your ambulance is a crime scene. It has to be cleared. But if you deliver him to the hospital and say he just hasn't breathed, his last breath was a half hour ago, the doctor will say, he's dead now. But your ambulance is clear. It's an important thing they taught us because we only had 2 rigs. If your ambulance is tied up at the hospital, you might not be able to serve the community. Okay. All of this because it's an important aspect of electricity, how the body works and how it uses, and being able to make these measurements of the voltage differences, the potential energy per unit charge, so that we can understand. Now, the heart's not the only thing. Oh, yes. A question just to see who paid attention. Okay, let's see if everything's going to work. Still not polling. Now it's polling. What part of the EKG is produced by the recovery or repolarization of the ventricles? That's good. The first 7 people all got it right. I asked this question because, of course, that's the one that was messed up for me. Okay, we all answered. 2 said the P wave, and 18 said the T wave. Yes, you answered. I got you. So, I went through, before I made this, I checked, and I'm pretty sure there is something that's a J wave. I don't even remember what it is. I didn't talk about those. I'm pretty sure they actually do exist. The P wave was the depolarization of atria. So that ain't it. Q wave is, these are part of the complex that are both repolarization of atria and depolarization of ventricles. And the T wave was our correct answer here that almost everybody got. That's the repolarization of the ventricles. I only have a minute. I am going to introduce a unit and then we'll go. That unit is a new unit for energy. It's called the electron volt. 1 electron volt is equal to 1 electron multiplied by 1 volt. Really complicated, right? So that's 1.602 times 10 to the minus 19 coulombs times 1 joule per coulomb is 1.602 times 10 to the minus 19 joules. So it's a standard energy unit if you think about it. Why do we use it? Because it's really simple. If I have a charge and the charge goes through a voltage difference, then change in potential energy is Q delta V. Change in kinetic energy is minus Q delta V. And so we can just say if I have a charge of minus 1 electron go through a voltage difference of plus 10 volts, it's going to end up with a kinetic energy increase of plus 10 electron volts. So I don't have to pull out the calculator. We can do the calculations real quick to convert the energy gained or lost by going through a voltage difference in units of electron volts. So that's why we use it. Okay, have a fabulous Sabbath. I'll see you again on Monday.